everyone, and welcome. Today, we are going to crack the code on a mathematical symbol that, let's be honest, can look a little intimidating at first, but it's actually one of your best friends for taming really long, messy problems. We're talking about sigma notation, so get ready to see how we can turn painful, drawn-out additions into clean, simple, and powerful expressions. So here's what we've got on deck. First, you're going to look at the kind of problem that makes sigma so necessary in the first place. Then, we'll decode the symbol itself piece by piece. After that, we'll learn the basic rules of the road, unlock some seriously powerful shortcuts, and finally, see how this all connects back to some math you probably already know. Okay, so let's dive right in. Look, to really get why sigma is such a hero, you first have to meet the villain it was made to fight. Just needless, tedious complexity. No, really, think about it for a second. Your job is to write down the instructions to add up every single whole number from 1 all the way to 100. How do you even write that down clearly and, not have it take up a whole page? You'd probably end up with something that looks like this, right? You write the first couple of numbers, throw in some dots in the middle to say you get the idea, and then finish with the last two. I mean, it kind of works, but it's sloppy. And for mathematicians or scientists where being precise is everything, this just doesn't cut it. There has to be a better way. And that brings us to the hero of our story, the capital Greek letter sigma. This is the elegant solution we've been waiting for. This is the tool built from the ground up to handle exactly this kind of repetitive addition, but with precision and, frankly, a lot more style. At its core, that's all sigma notation is. It's a command. When you see that big sigma symbol, it's basically shouting an order at you. Sum up everything that comes next. You can think of it as the ultimate zip file for addition, letting you compress a huge instruction into one neat little package. Okay, so how does this command actually work? Let's break it down. The best way to think about it is like it's a little recipe or even a tiny piece of code. The big sigma symbol is your main command, sum. Then you've got the index, which is usually a letter like I or K. That's your counter. It just keeps track of which step you're on. Down below, the lower limit tells the counter what number to start at. Up top, the upper limit tells it where to stop. And finally, the expression on the right is the actual recipe. It tells you what to do with your counter at each and every step. The whole thing is one complete, self-contained instruction. All right, so now we know how to read it. Let's get into the rules of the road. These basic properties are what makes sigma so incredibly useful, because they let us take big, ugly-looking sums and break them down into pieces that are much, much easier to handle. There are two main rules you've absolutely got to know. First up is the constant multiple rule. So let's say you're adding up 3 times I from 1 to 5, right? That's 3 times 1 plus 3 times 2 plus 3 times 3 and so on. You see how every single term has a 3 in it? This rule says you can just pull that 3 out front, do the simple sum first, so 1 plus 2 plus 3 plus 4 plus 5, and then multiply the whole thing by 3 at the very end. It saves so much work. Then you've got the addition and subtraction rule. If your expression is something like I squared plus I, you can actually split that one big problem into 2 smaller ones. Just find the sum of all the I squareds first, then find the sum of all the I's, and just add your 2 answers together. It's that classic divide and conquer strategy, and it is essential for tackling harder problems. Okay, if those properties were our basic toolkit, then these formulas, these are the supercharged power tools. These are the unbelievable shortcuts that let you solve massive summation problems without actually adding anything up. I mean, this is where sigma goes from just being a neat way to write things down to being an absolute beast of a computational tool. All right, check these out. The first one is pretty obvious. If you add a constant, c, to itself n times, you just get c times n. Makes sense. But that second one, the sum of I, that's the one. That's our golden ticket. It's the direct answer to that hand-cramped problem from the beginning. To add every number from 1 to 100, our n is 100. So we just plug it into the formula. 100 times 100 plus 1, all of that divided by 2. That's 10,100 divided by 2, which is 5,050. Boom, done. We just added up 100 numbers without doing a single bit of addition. I mean, how cool is that? That's the power we're talking about. So this is great for these kinds of problems, but where does it connect to other stuff you might have seen? Well, let's take a look at how sigma is the perfect language for talking about the sums of sequences. And this is a really cool connection. You might remember from school learning about arithmetic sequences where you add the same amount each time, and geometric sequences where you multiply each time. And you probably learned 2 completely separate, different-looking formulas to find their sums. What's so brilliant about Sigma is that it unifies all of this. It gives you one single consistent language to write the instruction sum the first n terms, no matter what the pattern is. It shows you that they're really just two different flavors of the exact same idea, a summation. There's this great quote that I think just nails the whole point of Sigma. It wasn't invented to make things look complex and scary. It was invented to take something that is incredibly complicated, like adding up a million numbers, and make it beautifully, powerfully simple. So, if you walk away with one thing today, let it be this. Sigma notation is way more than just a space saver. It's a fundamental change in how you think. It lets you stop focusing on the tedious step-by-step process of adding and lets you start thinking about the entire concept of the sum as a single object that you can actually work with.
We've seen how Sigma is this incredible tool for mastering the sum of a finite list of things, no matter how long that list gets. But of course, that opens up a really mind-bending question, doesn't it? What happens if that upper limit isn't 100 or a million or a billion, but infinity? What happens when the sum literally never ends? Well, that's your ticket into the wild world of infinite series and calculus. It's a story for another time, but the entire journey starts right here with understanding this one powerful symbol. Thanks for tuning in.